All right, looks like someone's been doing their homework. You sent over a ton of stuff on machine learning, articles, diagrams, charts, the works.
Wow, someone's eager to dive into the world of algorithms.
Yeah, this listener clearly wants to get a handle on choosing the right machine learning model for different situations. It can be pretty overwhelming to know where to start.
Absolutely. There are so many tools in the machine learning toolbox. But like any toolbox, you got to know which tool is for which job.
Right. It's like having a pantry full of ingredients, but no clue what to cook. Speaking of ingredients, there's a lot here about predicting continuous values. Things like house prices or stock prices. What's that all about?
Predicting a number that can fall anywhere on a scale, huh? That's where we get into regression techniques.
Okay, regression, like trying to figure out what a used car is worth.
Exactly. There's so many things that could affect that price. Mileage, age, condition.
Right. The price could be a few $100 or tens of thousands of dollars.
Exactly. So you need a model that can capture those subtle relationships between all those variables and then predict the price, a number that could be anywhere on that scale. One of the simplest is linear regression.
Linear, Cran. So it's basically drawing a straight line through the data.
You got it. Finding the best fit line to represent the overall trend. But sometimes the relationship between the variables isn't a straight line. Like think about predicting how a plant grows over time.
Oh, right. That wouldn't be a straight line at all. It'd probably start slow, speed up, then maybe level off.
Exactly. That's when you'd need something like polynomial regression. It can fit a curve to the data, not just a straight line. And there are even more specialized regression techniques like support vector regression or decision tree regression.
So many choices. It's like trying to pick a type of coffee light roast, dark roast, French press, espresso. How do you even know which one's right?
Haha. Good analogy. Just like coffee, it all comes down to your taste. Well, I mean, it depends on the problem you're trying to solve, the data you have, and how accurate you need to be. But don't worry, we'll get into the nitty-gritty of choosing the right model a bit later.
Okay, good to know. So we've talked about predicting numbers on a scale. What about when you need to categorize things? Like deciding if an email is spam or not.
That's classification. Think of it like sorting your laundry. You're separating clothes into different piles.
So spam or not spam. That's like whites and colors.
Exactly. Binary classification. Only two categories. But think about sorting your entire wardrobe, not just laundry. Shirts, pants, socks, underwear.
Right. That's multiclass classification. Way more than two categories.
You got it. And there are different ways to approach multi-class problems. Like you could do 1v1 where you create a separate model for each pair of categories.
So shirts versus pants, shirts versus socks, pants versus socks.
Yeah, or you can do 1v all. Each model tries to distinguish one category from all the others combined. Like, is this item a shirt or something else?
Okay, I'm getting the hang of classification. So we've got predicting numbers, sorting things into categories. What other tricks can these machine learning models do?
Well, have you ever wondered how streaming services recommend movies you might like? Or how online stores know what products to suggest to you? That's usually powered by clustering.
Clustering. It's about grouping things together based on how similar they are.
Exactly. Imagine you have a scatter plot of data points and you want to find natural groupings. Clustering algorithms try to figure out those clusters based on how close together the points are.
So if I have data on customer shopping habits, clustering could group together customers who buy similar products or shop at similar times.
Exactly. And there are all kinds of clustering algorithms. You've got partitioning clustering, which divides the data into a fixed number of clusters.
Like dividing a map into different regions.
Yeah, exactly. Then you have hierarchical clustering, creating a tree-like structure with smaller clusters nestled within larger ones.
Kind of like a family tree with branches and sub-branches.
Exactly. And then there's density-based clustering, which looks for areas where data points are densely packed together. Think of it like identifying clusters of stars in the night sky.
That's a cool way to think about it. So clustering helps you find hidden patterns and groupings. It's like a machine learning detective that helps you make sense of it all.
That's a great way to put it. And once you know those clusters, you can do all sorts of things. Personalize recommendations, target your marketing, even uncover new scientific insights.
This is fascinating stuff. But I have to admit, my head's spinning a little with all these model types. Is there any way to simplify things?
One way to make your models more powerful and accurate is with ensemble methods. Imagine you're not just relying on one expert, but a whole team of experts.
So it's like getting a second opinion or a third or a 100th.
Exactly. Ensemble methods combine multiple machine learning models to make a more robust prediction. One popular technique is called bagging, which stands for bootstrap aggregating.
Bootstrap aggregating, Dot. Sounds intense. What's actually happening there?
Okay, so imagine you have a data set and you create multiple smaller data sets by randomly sampling from it. Then you train a separate model on each of those smaller data sets.
So it's like making mini versions of the original data and training a model on each one.
Exactly. And to make a prediction, you combine the predictions of all the individual models. It's like having a panel of judges, each with their own perspective, and then you average their scores to get a more reliable result.
Makes sense. So bagging creates diversity in the models and combines their wisdom. What other ensemble methods are out there?
There's boosting. Imagine you start with a simple model and it makes some mistakes. Boosting then focuses on those mistakes, giving more weight to the data points it got wrong.
So the model is learning from its errors and trying to do better on the tougher cases.
Exactly. You can even repeat this, building a whole sequence of models, each one trying to correct the errors of the previous one. It's like having a coach that keeps pushing you to improve.
I like that. Boosting is like personal training for your machine learning model.
Yeah.
Any other ensemble methods we should know about?
Well, there's stacking, which is like building a supermodel that learns how to combine the predictions of several other models. It's like a conductor leading an orchestra.
So stacking is like creating a meta model to orchestrate all the other models.
Exactly. And then there's cascading, where models are arranged in a sequence, each one handling tougher cases. It's kind of like a triage system at a hospital.
Okay, I'm starting to get the power of ensemble methods, combining the strengths of different models to create something even stronger.
You got it. And they're used everywhere. Fraud detection, medical diagnosis, self-driving cars. They're a real workhorse in machine learning.
This is mind-blowing. Okay, we've covered so much regression, classification, clustering, ensemble methods, but I can't let you go without talking about neural networks. They're like the rock stars of AI, right?
You could say that. Inspired by the human brain, they're behind some of the biggest advances in AI. Image recognition, natural language processing, the whole shebang.
So how do they actually work? Are they like little brains in a computer?
Not quite mini brains, but they do have similarities. They consist of layers of these interconnected nodes, or artificial neurons. Data goes in one end, gets processed through these layers, and then an output comes out the other end.
So it's like data flows through a network of nodes, kind of like signals traveling through neurons in our brains?
Exactly. And the connections between those nodes have weights that are adjusted during training to learn patterns. The more data you feed it, the more it learns, and the better its predictions become.
So it's kind of like those connections in our brains getting stronger as we learn new things.
You got it. And there are different types of neural networks, each good for certain tasks. There are artificial neural networks, ANNs, which are like the foundation. Then there are convolutional neural networks, CNNs, which are rock stars at image recognition.
CNNs, so they're like the visual artists of the neural network world.
Exactly. They use special layers to extract features from images so they can identify objects, patterns, even emotions in pictures.
That's amazing. So when I upload a photo to Facebook and it automatically tags my friends, that's probably a CNN at work.
Most likely. Then there are recurrent neural networks, RNNs, which are designed for handling sequential data like language. They have these looping connections that allow them to remember past information. Really important for understanding the context of words and sentences.
So RNNs are the wordsmiths of the neural network world.
You could say that. They power things like language translation, speech recognition, even chatbots. And then there are LSTMs, long short-term memory networks. They're a type of RNN that can remember things for longer periods.
So if RNNs are the wordsmiths, then LSTMs are like novelists, weaving together those long, complex stories.
That's a great way to put it. They're great at language translation, where remembering information from previous sentences or even paragraphs is super important.
It's incredible how different neural network architectures specialize in different types of data. But how do they actually learn? How do they know which connections to strengthen and weaken?
That's where activation functions come in. They add nonlinearity into the network, which allows it to learn those complex patterns. Without them, it would just be a bunch of linear transformations, which wouldn't be very powerful.
So they're like the secret ingredient in the neural network recipe.
Exactly, and there are tons of different activation functions, each with its own pros and cons. ReLU, sigmoid, tan are a few of the popular ones. The choice depends on what you're trying to do and the structure of your network.
It sounds like designing a neural network is like baking. You need the right ingredients and the right recipe to make something amazing.
That's a great analogy. Just like baking, there's a lot of experimentation and tweaking involved to get the best results. But what's really cool is that they can learn complex patterns without explicit instructions.
That's incredible. There are two more fascinating types of neural networks that are worth mentioning. deep belief networks, or DBNs, and generative adversarial networks, or GANs.
Absolutely. DBNs are like the building blocks for more complex networks, and they are used for unsupervised learning, which means they don't need labeled data for training. They learn to represent data in a hierarchical way, extracting features and patterns without being explicitly told what to look for.
So they are like the self-taught prodigies of the neural network world.
Exactly. Then we have GANs, which are like a creative duo of neural networks, a generator and a discriminator that compete against each other to generate realistic new data.
Can you expand on the generator and discriminator?
Of course. The generator tries to create data that fools the discriminator, while the discriminator tries to distinguish between real and fake data. This adversarial process results in incredibly realistic outputs, such as images or music that are nearly indistinguishable from the real thing.
That's mind-blowing. So GANs are like the artists and critics of the neural network world, always pushing each other to create more impressive works.
That's a great way to think about it. GANs have opened up a whole new world of possibilities for AI, blurring the lines between human creativity and machine learning.
This is seriously amazing stuff. We've covered a ton already: regression, classification, clustering, ensemble methods, and now neural networks. Machine learning is a vast, rapidly evolving field with mind-blowing potential to change everything.
Absolutely. And we've barely scratched the surface. There's a universe of possibilities
I
out there.
know, it's a bit overwhelming, but exciting at the same time. Let's take a step back for a second. Remember, your big question was how to choose the right model for a specific problem. There are just so many options.
That's a great point. Choosing the right model is like being a detective. You need to gather clues and put the pieces together. And your first clue is understanding the nature of your data.
Okay, so what kind of data clues should we be looking for? What do we need to consider when deciding which model to use?
Well, the first thing to ask yourself is whether your data is labeled or unlabeled. Labeled data means each piece of data comes with a tag or category, like images labeled as cat or dog, or customer reviews labeled as positive or negative. Unlabeled data doesn't have those predefined categories.
So if I'm trying to build a model to recognize different types of flowers, and I have a data set where the flower pictures are already tagged with their species, that's labeled data.
You got it. That means you could use supervised learning algorithms like classification. But if you just had a bunch of flower pictures with no tags, you might need to use unsupervised learning techniques like clustering to group similar flowers together first.
Got it. So the type of data dictates the type of learning we can use. What other data clues are important?
Think about what type of data you have. Is it numerical, like stock prices, categorical, like colors or species, or something more complex, like text or images?
Right, because a model designed for numbers wouldn't be good at understanding language.
Exactly. Each type of data has its quirks, and you need specific algorithms for each. Numerical data. Regression's often a good starting point. Categorical data. Decision trees or support vector machines might be good choices. And for text or images, deep learning models like those neural networks we talked about really excel.
Okay, so data type is a big factor. But what about the problem we're trying to solve? How does that play into our model choice?
The problem type is your second big clue. Are you trying to predict something, like future sales or whether someone will click an ad, or are you trying to discover patterns and group things together, like in customer segmentation?
So if I'm a business owner and I want to forecast demand for my product, that's prediction, right? Whereas if I'm a marketing manager trying to identify different customer groups, that's pattern discovery.
You got it. And those different problem types lead you to different families of models. Prediction often involves regression or classification, while pattern discovery leans towards clustering or association rule mining.
This is starting to feel like a real detective game. What if I have a problem that involves both prediction and pattern discovery? Like, I want to predict which customers are likely to leave and understand what makes those customers different.
That's when things get interesting. You might need to combine different models or try something more advanced like reinforcement learning, where an agent learns by interacting with its environment and getting feedback.
Whoa, reinforcement learning sounds intense. We'll have to dive into that another time. But for now, let's stick to the basics. Data type, problem type. What else should we be thinking about when choosing a model?
Accuracy is always important. You want a model that makes good predictions or finds meaningful patterns. But often there's a trade-off between accuracy and interpretability.
Interpretability. What does that mean in this context?
It's about how easy it is to understand why a model makes certain predictions. Some models, like linear regression or decision trees, are pretty transparent. You can follow their logic.
So it's like being able to see under the hood and understand how the engine works.
Exactly. But other models, especially deep neural networks, can be more of a black box. They might be super accurate, but it's hard to figure out what's going on inside.
So it's like having a brilliant AI giving you amazing answers, but you have no clue how it came up with them.
That's the dilemma. And whether you choose accuracy or interpretability depends on what you need. If you need to explain the model's decisions to your boss or regulators, interpretability is crucial.
That makes sense. If I'm using a model for medical diagnosis, I want to know why it's recommending certain treatments. But if I'm just trying to optimize ad clicks, maybe interpretability isn't as important.
Exactly. And there are ways to make even complex models more interpretable, like feature importance analysis or using surrogate models. But that's a whole other topic.
Let's save that rabbit hole for another time. So we've covered data type, problem type, accuracy, interpretability, anything else.
Don't forget about practical things like how much computing power you have and how much time you have. Some models are much more computationally intensive than others. Deep learning, for example, can need a ton of data and processing power.
Right. So if I'm on a tight budget and deadline, I might need to go with a simpler model, even if it's a bit less accurate.
Exactly. And don't underestimate the importance of getting your data ready and engineering good features. You know what they say, garbage in, garbage out. Even the fanciest model won't work well if it's fed bad data.
It's like having a state-of-the-art kitchen, but only using spoiled ingredients. No Michelin stars for that.
Perfect analogy. Actually, speaking of food, I'm starting to feel a bit hungry.
Me too. All this machine learning talk has worked up an appetite for knowledge and for actual food. Let's do a quick recap before we take a break, though. We talked about different types of models, like regression for predicting those continuous values and classification for sorting things into categories.
Right, and we touched on clustering for grouping similar things together.
And remember those ensemble methods, combining multiple models to boost accuracy.
And of course, those neural networks, inspired by the human brain, doing some seriously impressive stuff.
Okay, we're making progress. But before we get into the details of choosing the right model for different situations, let's take a break and refuel. We'll be back to continue our machine learning deep dive shortly.
Welcome back. Hope you grabbed a snack. We've got more machine learning insights coming your way. Ready to get back to choosing the right model for the job.
Absolutely. I'm feeling refreshed and ready for some real-world examples.
Perfect. Let's start with music. Imagine you're a music streaming service, and you want to recommend songs to your users. What kind of machine learning would you use for that?
Ooh, that's a good one. It's like playing matchmaker, but for music. I guess you'd need to figure out what each user likes and then recommend songs that match their taste.
Exactly. And that's where something called collaborative filtering comes in. It looks at patterns and user ratings to recommend songs enjoyed by others with similar tastes.
So it's like, hey, if you like these 10 songs, you might also like this other one that people with similar tastes loved.
Right. But how does it know which users have similar tastes?
Yeah, how does it figure that out?
That's where clustering comes in. Remember we talked about grouping similar things together? Well, here, those things are users, and those similarities are based on their listening history and ratings. Like, the model might group users who listen to a lot of 80s pop, or users who love classical music, and so on.
Ah, so clustering helps the model make these taste-based groups, and then collaborative filtering uses those groups to make the recommendations.
You got it. And the more data you feed the model ratings, listening history, even things like time of day or location, the better those recommendations become.
That's cool. It's like having a personal DJ that knows your taste and keeps learning more about you. Okay, let's switch gears. What about a business trying to predict customer churn? Trying to prevent those cancellations that can really hurt a company.
Churn prediction is a huge deal for a lot of businesses, and it's a classic classification problem. Remember, sorting things into categories. Here, we're trying to figure out which customers are likely to stay and which are likely to leave.
So you need a model that can analyze customer data and predict whether they're going to stick around or say, see you later.
Exactly. What data you'd use depends on the business and their customers. It could be purchase history, website activity, customer service calls, demographics.
Wow, that's a lot of data. Once you have it, how does the model actually make a prediction?
One common technique is logistic regression. It's a type of classification algorithm that predicts the probability of a customer churning based on a bunch of input variables.
So it's calculating the odds of someone canceling.
Yep. And if the business understands what's causing churn, they can try to keep those customers. Maybe they offer a discount, better support, or recommend different products or services.
It's like using machine learning to build a customer safety net. Okay, one more scenario. Imagine you're a medical researcher trying to develop a model that can diagnose a disease based on patient data.
Now that's a powerful application of machine learning, and it often involves a combination of techniques depending on the data and how complex the disease is.
What kind of data are we talking about here?
It could be patient symptoms, medical history, lab tests, genetic info, even images like X-rays or MRIs.
That's a lot for the model to process. How does it even start making sense of it all?
Well, for structured data like demographics or lab results, you might use decision trees. It's like a flowchart of questions and answers leading to a diagnosis.
So, like, if the patient has this symptom and this test result, then it's probably this diagnosis. But if they have a different symptom, then it's something else.
Exactly. Very intuitive for modeling decision making. But with more complex data, like medical images, you need something more powerful, like a convolutional neural network.
Those visual artists we talked about. Good at spotting patterns in images.
Exactly. CNNs can be trained to see things in medical images that even a doctor might miss, leading to faster, more accurate diagnoses.
Wow, so machines could help doctors make better diagnoses and save lives.
It's already happening. Machine learning is revolutionizing healthcare. Personalized medicine, drug discovery, robotic surgery.
This is seriously cool stuff.
Okay.
My brain's feeling a little full. I need a minute to digest all this.
I hear you. We've covered a ton. It's like a whirlwind tour of the machine learning landscape.
It is. But I'm starting to see the bigger picture. Machine learning isn't just about algorithms and technical stuff. It's about solving real-world problems, recommending music, predicting customer churn, diagnosing diseases.
Exactly. And the key is choosing the right tool for the job. It's like having that toolbox full of specialized tools.
And that's what we've been doing today, figuring out what those different tools are and when to use them.
You got it. We talked about beta type, problem type, accuracy, interpretability, computational resources.
Right, it's like a mental checklist to go through before even starting to build a model.
Exactly. And once you've thought about all that, you can start digging into specific algorithms and techniques that might be a good fit for your problem.
This has been an amazing journey. But before we go any further, I'm curious about your thoughts on the future of machine learning. What are the most exciting things on the horizon?
That's a great question. One of the most exciting areas is the development of even more powerful and efficient deep learning models. Researchers are constantly pushing the boundaries of what's possible with neural networks, creating models that can handle even more complex data and tasks.
So we're talking about even smarter AIs that can understand language, recognize images, and make predictions with incredible accuracy.
Exactly. And those advances are driving innovation in tons of industries, healthcare, finance, transportation, everywhere. We're also seeing a lot of interest in explainable AI, making those models more transparent so we can understand what's going on inside.
So it's not just about having a black box AI, but also understanding how it makes decisions.
Right. Explainable AI is super important for building trust in these systems and making sure they're used ethically. Another exciting trend is edge AI. Running machine learning models directly on devices like smartphones or sensors instead of in the cloud.
So bringing AI closer to where the data is.
Exactly. Edge AI means faster processing, less lag, and better privacy because the data stays local. It's changing the game for things like self-driving cars, smart homes, and wearable health trackers.
This is all so fascinating. Machine learning is constantly evolving and pushing the boundaries of what's possible.
It is. And the best part is we're still in the early stages. There's so much more to come.
This deep dive has been incredible. We explored different types of models, how to choose the right one, and even got a glimpse of the future.
And we did it all without getting lost in too much technical jargon.
Right. Just like a chat between two friends excited about learning new things. Before we wrap up, any key takeaways for our listeners who want to start their own machine learning adventures?
Remember, choosing the right model is all about experimenting, trying things out, and refining your approach. Don't be afraid to explore different options.
Just like a chef experimenting with new ingredients and recipes.
Exactly. And good data is crucial. Your model is only as good as the data it learns from. So spend time cleaning, prepping, and really understanding your data before you even pick a model.
Garbage in, garbage out. We've learned that one for sure.
Yeah.
Any other words of wisdom?
Don't be intimidated by machine learning. There are so many resources to help you get started, online courses, open source libraries, everything. The most important thing is to be curious and keep learning. AI is changing all the time, and there's always something new to discover.
So stay hungry, stay foolish, and keep exploring. Thanks for joining us on this machine learning deep dive. Okay, I think I've digested all that. My machine learning brain is ready for more.
Great. We've got a good understanding of different machine learning models and what to consider when choosing one. Let's put that knowledge to work with some more real-world scenarios.
Sounds good. Let's get practical. What kind of situations would call for different models?
All right, imagine you work for a bank and you want to build a model to detect fraudulent credit card transactions. What kind of problem is that?
Well, you're trying to predict if a transaction is fraudulent, so it's definitely about prediction. And there are only two possibilities, fraud or not fraud, so it's a binary classification problem.
You got it. And because financial data is often very structured and numerical, you might want to use something like logistic regression or a support vector machine. They're good at analyzing patterns in numbers and making those binary classifications.
So the model would look for anything suspicious in the transaction data. Unusual spending patterns, different locations, weird merchant categories, and use those to predict if it's fraud or not.
Exactly. And machine learning can spot those subtle patterns that humans might miss. Faster and more accurate fraud detection.
It's like having a superpowered fraud detective. Okay, let's try a different industry. What about a retail company that wants to personalize their marketing? How can machine learning help with that?
Personalization is all about knowing what each customer likes and tailoring your message. That's where clustering shines.
So you could group customers together based on their buying habits, what they browse online, their demographic.
Exactly. Then, once you've got those groups, you create marketing campaigns that speak directly to each group's interests. Like you could send emails with products that are popular within that specific group, or adjust the style of your ads to match their demographics.
It's like having a whole team of marketers, each one focused on a different customer group. Way better than sending everyone the same generic message.
You got it. Personalization gets people more engaged, more likely to buy, and ultimately happier with their experience.
Okay, last scenario. Let's say you're working for a transportation company and you want to find the best delivery routes to save fuel and time. Can machine learning help with that?
That's a classic optimization problem, and there are a few ways machine learning can tackle it. One approach is reinforcement learning. An agent learns to make decisions in a changing environment by getting rewards or penalties.
So the agent is like a virtual delivery driver, and it gets rewarded for being efficient and fast.
Exactly. The agent would try different routes and learn from its mistakes. Eventually, it figures out the most efficient way to do things, considering things like traffic, deadlines, and how much the truck can carry.
It's like a super smart GPS that's always learning the best routes.
Exactly. And by optimizing those routes, the company saves money on fuel, gets deliveries done faster, and keeps customers happy.
This has been an incredible journey. I feel like I've learned so much about how machine learning can be used to solve all kinds of problems.
Me too. And remember, this is just the beginning. Machine learning is constantly evolving. There's always more to learn and explore.
I'm definitely feeling inspired to keep learning. Any final words of advice for our listeners who are ready to embark on their own machine learning adventures?
Stay curious. There are tons of interesting problems to solve and creative solutions out there. Ask questions, experiment, and enjoy the learning process.
That's great advice. Never lose that curiosity and that drive to learn new things.
Absolutely. And don't let the technical stuff scare you. There are so many resources to help you get started, no matter your skill level. User-friendly platforms, online tutorials, communities, that you name it. The most important thing is to have a passion for problem solving and a willingness to learn.
That's a great point. It's not just for tech experts, it's for anyone who wants to learn.
Exactly. And as machine learning becomes even more accessible, we'll see even more people from all walks of life using it to solve problems and make a difference.
That's an inspiring thought. So to all our listeners out there, no matter your background, dive into the world of machine learning. You might discover a hidden talent, a new passion, or a way to make a real impact.
Couldn't have said it better myself. Remember, the learning journey is just as important as the destination. Embrace the challenges, celebrate your wins, and keep exploring.
Thanks for joining us on this deep dive into machine learning. We hope you've enjoyed the ride and feel inspired to continue your own exploration. Until next time, keep learning, keep growing, and keep pushing the boundaries of what's possible.